Alrighty, let's talk about the concept of life and biochemistry. So, life, of course, is what we study as biologists, and it's this amazing thing, this mysterious thing. We could talk about, we will a little bit later, about what it is that makes something alive. And let's mention a little now. I mean, we feel like we can distinguish between living and non-living things. I look at me and I say, I am probably a living thing. This is probably not. But why? What's the difference? Well, we could come up with a list of things that are commonly seen in living things that are often not seen in non-living things. We could say that living things, we could say that they reproduce. Most, I mean, not all. If I never had children, I'd still be a living thing, but I have probably the capability of reproduction, although a person who doesn't is still alive, so that's kind of maybe. But in general, living things reproduce. They metabolize. Living things take in materials from the world and then alter them in some way. They do something with them. We can say that they grow. We can say that they respond to the environment. All of those things are characteristics of living things, or at least many living things. And there are some things that are kind of on the border. For example, we could talk about viruses. Viruses can't reproduce on their own, but they can hijack other living systems and use their machinery to reproduce. So that's kind of like reproduction. They don't metabolize. They don't take in molecules and use them for energy or that, but they do direct cells to do that on their behalf. They themselves do not grow. And really, outside of cells, they don't respond to their environment. On the other hand, they do evolve. Individual viruses don't, but a population of viruses can. So, are they alive? Well, there isn't universal agreement on that. Some people say yes, some no. And we could have some interesting discussions about that. But right now, let's look at this and say, so what is it that makes something alive? How does a living thing do all these things? Well, as far as we can tell right now, there really isn't any sort of magic to it. There isn't a life force as far as we can tell. There's nothing fundamentally different, no mysterious thing happening in a living thing as compared to a non-living thing. That's not to say that living things aren't amazing and wonderful to study, but as far as we can tell, life comes from having the right biochemistry. And all life that we know of seems to involve complex chemical reactions in a water solution. There are some interesting thoughts about whether it would be possible to have living things that didn't use water as their basis. We've never seen one, but it might be possible. But from what we have seen so far in the world, all life that we can identify involves a complex set of chemical reactions happening in water solution. So to understand human physiology, we need to understand a little bit about that chemistry. So for the first parts of this, for these core concepts lectures, we're going to be talking a lot about the molecular biology that happens in living things. And that is going to inform a lot of the rest of the course. We'll be talking a lot about what happens at the molecular level. So, in order to understand, one thing that's in common between all living things is that they seem to happen in water. So we're going to approach to what we're doing right now largely in the context of why do some molecules interact with water in some ways and others interact in other ways. We're going to get into the idea of hydrophilic and lipophilic, which are really important key concepts to understanding a lot of what happens in physiology. But to understand that, we have to go even further down and talk about the structure of atoms and the basics of chemistry, why atoms interact with other atoms. So that's where we're going to go with this right now. We're going to be talking about atomic structure and how atoms interact. All right, let's talk about the structure of an atom. Now, atoms are the smallest Well, they're not actually the smallest unit of matter. We're going to be talking about things smaller than atoms, but they're the smallest unit that interacts in a way that we recognize as chemistry. So let's talk about the structure of an atom. So in the center of an atom, we have a small dense area called the nucleus. That is going to contain at least one proton. Protons are very, very tiny particles. They carry 1 unit of positive charge. So sometimes I've had students say, so what is electrical charge actually? And my answer is, I really do not know. At a fundamental level, I do not understand what electrical charge is. It's a property that matter can have that affects how it interacts with other matter. If you want to know more, talk to a physicist who can talk to you about quantum mechanics. But what I can tell you is that some things have electrical charge. And electrical charge comes in 2 types, positive and negative. Protons are small particles that carry 1 unit of positive charge. They're found in the nucleus of an atom. Now, the nucleus may also contain 1 or more neutrons. Neutrons are particles that have very nearly the same mass as a proton, but carry no electrical charge. They are not actually required in the nucleus. Most hydrogen atoms do not have a neutron, but just about I think as far as I can tell, all other atoms do. What exactly they're doing there seems to have something to do with stabilizing the nucleus. We can mention that in just a moment here. So what we've got here is a nucleus which carries a positive charge. Now, electrical charges are very powerful. And if all I had was a nucleus, just this little positively charged thing, it would be so strongly attracted to any other negatively charged thing that it really couldn't behave on its own. It would just zip to the nearest negatively charged thing it could find. So in order for this to be any sort of independent thing, we need some sort of negative charge to balance out this positive charge. I'm going to remove that neutron for now. Actually, I will leave it. So, where do we find the negative charge? Well, for that, we're going to look outside the nucleus. Let me see if I guess I don't have a green marker right now, so I'll use blue. So somewhere outside the nucleus, we're going to have another kind of particle, an electron. Electrons are much smaller than protons and neutrons. There's actually, my understanding is there is some debate about whether they have any meaningful physical size at all, or whether they're more of just sort of an abstract point entity. If you've ever taken basic quantum mechanics, try to do so at some point. There is weird stuff that goes on here. For example, these electrons are difficult to describe as a particle exactly. They also show strong characteristics of being a wave that has mathematical characteristics about where it is around this, and you can't exactly say where. Weird. But wonderful weird stuff. Anyway, back to this. So these electrons carry 1 unit of negative charge. So if I have here 1 proton and 1 electron, those 2 charges balance each other out. So this system, 1 proton and 1 electron, is electrically neutral. It has no overall charge. It's not positive or negative. Overall, it's neutral. Now, since these 2 things have opposite charges, you would figure they're going to attract each other and go whomp and just come together. But that's not really the way it works. The electron does not come right up to the proton. Instead, it kind of moves around in the space around it. How exactly that works, again, is complicated. It's best described probabilistically. You could say, what's the chance that you'll see the electron here, or here, or here, or here, or here? And you get some interesting stuff with that. But let's just redraw this over here. Actually, I'm going to draw a slightly different atom. We're going to draw an atom with 2 protons and 2 neutrons in its nucleus. So you know, by the way, the atomic number of an atom is the number of protons. So this atom has atomic number 2. That also tells you what element it is. Atoms with atomic number 2 are of the element helium. Now, if this nucleus has 2 protons, it has a total 2 positive charges. So how many electrons would this atom have to have in order to be electrically neutral? As far as I can tell, it would have to have 2. 2 units of negative charge would balance those 2 units of positive charge. Being electrically neutral is not strictly required. You can have an atom that is not neutral, but being neutral is much more stable than not being neutral. So atoms have a strong tendency to be neutral. There are reasons why they might not be, and we'll get to that. That's extremely important. But right now, if this is going to be neutral, it's going to need 2 electrons. Now, we often show these electrons sort of orbiting around the nucleus like little planets, and that's not actually how they work. But it is a convenient way to show it at this level. If you have taken chemistry, or if you're going to take chemistry, you'll learn more of the subtleties about orbitals and how that really works more. But right now, we're just going to think about them in little orbits. And we can really talk about them being in different kind of layers around the atom. These electrons will arrange themselves in, sometimes you call them shells or energy levels. Orbitals is another term, although there are some subtleties to that. I'm just going to call them shells for now. Electron shells. Now, how many electrons can fit into each shell? That's another interesting question. And there's a specific number. The first shell, the first layer of electrons around an atomic nucleus, can only hold 2. So first shell can hold 2. Since this one needs 2 electrons, we'll just put them in there. 1, 2. And there we have it. There is our neutral helium atom. Its first electron shell is full. It has 2 in it. Whatever the outermost shell is, we call the valence shell. And we call the electrons in that shell the valence electrons. Since this only has 1 shell, that is the outermost shell. So helium has 2 valence electrons. We talked about how being neutral makes atoms more stable. So let's talk about things that make atoms happy. Happy, of course, is not the term. Atoms are not conscious entities as far as we can tell. They do not have emotions. They are not happy or sad. But we can sort of use this as an anthropomorphization of this. What we mean really here is stable. So things that atoms tend to want to move toward. Again, want being the wrong word, but set that aside. So, things that make atoms happy. Being neutral and having a full valence shell. Those are 2 things that atoms try to achieve. This one gets both. We have a neutral helium atom here, 2 protons, 2 electrons, so it's electrically neutral, and its valence shell is full. It has the 2 electrons that it can hold. Helium is very happy on its own, which is the main reason why helium atoms do not really interact with any other atoms. They have no need to. They're sort of self-contained. They've got everything they already need, so they almost never interact chemically with other atoms. It's very rare to find helium compounds. Never. So, helium, if that was all it was, this would be terribly boring. So let's look at something that's a little less boring. Let's erase this stuff. And talk about an atom which doesn't have a full outer shell. Let's talk about hydrogen. Hydrogen has 1 proton in its nucleus. It may or may not have a neutron. Most hydrogen does not. So most of it's just 1 proton. So how many electrons does it need to be full? To be neutral? 1. 1 proton, 1 electron. Electrically neutral. Does it have a full outer shell? No, there's its shell. That's the first shell. The first shell can hold 2. It has 1. That means that there is some aspect of hydrogen which is unfulfilled, which it has a deep and burning longing to have a full outer shell. It's just, there's something missing in hydrogen's life. Now, think about that compared with helium. Helium was sort of self-contained. It was neutral, had a full outer shell. It doesn't have to interact with anything. Hydrogen is neutral, but it does not have a full outer shell. This is why hydrogen is so much more reactive than helium. Hydrogen has a reason to interact with other atoms, and it does. You never find single atom hydrogen. You find hydrogen gas, but that's actually 2 hydrogen atoms bound together. We'll get to that. If you've ever heard of the Hindenburg disaster, it was a serious problem involving a relatively early blimp when they filled them with hydrogen, which unfortunately is extremely reactive and caught fire and exploded. Helium balloons don't do that because helium doesn't react with anything, almost anything. Anyway, so hydrogen wants to interact with something in some way. It wants that full outer shell. Now, it could get that hypothetically by taking on an electron from something else. If it got an electron, that would give it 2 in its outer shell, but then it wouldn't be neutral. So it'd be giving up being neutral in exchange for having that full outer shell. The hydrogen doesn't usually do that, but let's talk about an atom that does. Let's talk about sodium. Sodium has 11 protons. Atomic number 11. So how many electrons will it have? To be neutral, it has to have 11. So how are they arranged? Well, the first shell can hold 2. That's not enough. So the other ones now have to go into the second shell. How many can the second shell hold? Turns out, 8. So we've got 2, we need 11. So 3, 4, 5, 6, 7, 8, 9, there's 10 electrons. And now that shell is full, but I still need 1 more electron. But that shell's full, so gotta go to my third shell. There's my 11th electron. How many can the third shell hold? Well, that's a slightly complicated thing. We're gonna say 8 with a little star. At 8, it acts like it's full, and we start to fill the fourth one. But if you keep adding electrons, eventually you go back and start adding more to the third shell in a weird way. So for our purposes, 8. The atoms where that's important are less common, although certainly exist in biochemistry. Anyway, but certainly 1 can fit in that shell. So here's my sodium atom. 11 protons, 11 electrons. It's electrically neutral. That part of its life is fulfilled. But does it have a full outer shell? No. It's only got 1. It would like 8. It's missing 7. That's terrible. Adding 7 electrons to this would be effectively impossible. If you stuck 1 more electron in here, you'd have 2 in the outer shell, and now it's carrying a negative charge overall. Now it's got 12 electrons and 11 protons. Overall electrical charge is 1 negative. Putting another negative on there, since like charges don't go together well, you'd have to get another negative charge on this already negatively charged thing, and you're still not giving a full outer shell. Never going to happen, let alone putting 7 more on here. So how could this get a full outer shell? Well, the easiest way would be to take that electron away. If you could find a way to get rid of that electron, you'd be left with 11 protons and 10 electrons, so it would have a positive charge, but that would leave it with this as its valence shell, and that would be full. So yes, it would be giving up, it would be getting a charge, but it would be getting an outer shell. Is that going to work? Well, it'll depend on what happens after that. But still, if I could find someone to take that electron, maybe that would be worth it. Who could take an electron away from a sodium atom? Let me introduce you to another atom. Chlorine. Chlorine has 17 protons in its nucleus. So let's set up its electrons. First shell gets 2. Second shell gets 8. That's 10. So third shell, 10. 11, 12, 13, 14, 15, 16, 17. Here is our neutral chlorine atom. 17 protons, 17 electrons. Electrically neutral, outer shell, wants 8, has 7. It's unfulfilled. If only it could get 1 electron. If only we could find an atom which would be willing to give up its electron in this case. Where could we find such a thing? If you put sodium metal, sodium, interestingly, I know we think of sodium as salt, but in its elemental form, it's actually a soft silvery metal. If you put sodium metal and chloride gas together and light a spark, you get a very impressive reaction. Here's what's happening in that case. Get these together, and my sodium, if you give it a little energy to start this, can surrender this electron, emptying that shell, and giving it to the chlorine there. Now, that leaves my sodium with 10 electrons and 11 protons, which means now it has a positive charge. I can write this. The elemental symbol for sodium is Na, from Latin word natrium, which is what they called sodium. We would call that Na+, sodium ion. An ion is an atom or molecule that carries an electrical charge. So sodium atoms, it's relatively easy to get them to become Na+. They can give up that 1 electron and become a positive ion relatively simply. So my chloride ion, when it takes that electron, also becomes an ion. Now it's 17 protons but 18 electrons, which means it's Cl, that's its elemental symbol, minus. And when it's that, we don't call it a chlorine ion, we call it a chloride ion. So if I put pure sodium, and elemental chlorine together, and give it enough energy to start this, they start transferring these electrons, and now I've got a positive sodium ion and a negative chloride ion. Remember, opposite charges attract, so let's see what's going to happen. Let's make these a little smaller. We'll make our sodium ion and our chloride ion. Chloride ion's a little bigger. So these two things will attract each other. Being opposite charges, they'll tend to stick together, which actually makes it easier for them. Yes, it's true that becoming an ion, becoming not neutral, is less stable, but if you can be an ion that has a balancing ion, an oppositely charged ion nearby, that's kind of okay. Because now at least you're not this lone positive charge, you've got a negative charge near you, likewise for the negative charge. So these two ions together are pretty stable. They stick together. And this electrical attraction between them is called an ionic bond. A bond between two ions. In fact, what you'll get with sodium chloride is lots of these things together in a pattern that looks like this. Repeat, going out. You get a crystal. This is table salt. So, table salt, the stuff you have that makes your food salty, is an ionic compound. It's a compound made of oppositely charged ions that stick together with these ionic bonds. It's very hard to get these apart normally. You can melt sodium. It is possible to take table salt and melt it, give it enough heat to break these apart and let them flow. But it's very difficult. A temperature needed is something like 1700 degrees Fahrenheit. It's a lot. It's really, really hot, like blast furnace hot. But it's also possible to separate them by putting them in a glass of water and stirring. Why would they come apart in water? That's kind of, honestly, that's kind of one of the key ideas in human physiology. Why does this interact so interestingly with water? Because what happens in molecular biology and living things is that you have a lot of different materials dissolved in water, separated from other molecules like them so they can interact with each other in water. So why does water do this? What's so special about water? That is what we're going to get to now. So we've just talked about how two atoms could interact in such a way that you get electrons moving from one to the other, you get two things of opposite charges which then stick together with an ionic bond. That is one way that atoms can interact. If you have something that easily gives up an electron and something that easily takes one, they tend to come together to make some kind of salt like this. And there's other ways that this can happen. But not everything can do that. So let's take a look at another way atoms can interact. Let's go back to looking at hydrogen. Hydrogen had one proton. I guess I should use a consistent color scheme here. One proton and one electron. I mentioned that you never find single atom hydrogen, what we call monatomic hydrogen. Never. What you will find is hydrogen molecules, two hydrogen atoms stuck together. But how would that work? Because this hydrogen atom certainly won't give up its electron, leaving it as a bare proton, at least not easily. So what's going to happen if I get two hydrogen atoms close together? The kind of interaction we just talked about won't work very well. For one of them to give up the electron to the other one, yes, this would become positive, that would become negative, but this would then have no electrons. Not good. But instead, there's another way these two things can interact. Rather than transferring electron from one to the other, they can share. So one hydrogen atom can provide one electron. The other hydrogen atom can provide a different electron. And the two of them can share a pair of electrons. These two electrons will now be moving around both of those nuclei, kind of joining these together into something that's not exactly just one atom anymore. It's what we call a molecule. So this is now a hydrogen molecule. These two atoms are sharing a pair of their valence electrons, of their outermost electrons. Because they're sharing a pair, a shared pair of electrons, we call a covalent, two valence things together, bond. Once they're sharing those electrons, it is relatively difficult, not impossible, certainly, but relatively difficult to get them to come apart, because this makes both of them more stable. Now, the whole thing together is electrically neutral. Two protons, two electrons, and each one feels like it has two electrons in its outer shell, so its outer shell is full. So these are both now happier than they were before. To separate them makes them less stable, less happy. You're going to have to put work into that and then give them something else to do to make them happy. But two hydrogen atoms can come together in a shared covalent bond, making a hydrogen molecule, which we would write as H2. This is the form in which you find hydrogen gas, in the diatomic hydrogen molecule. Great! Yay, hydrogen. Many atoms can come together this way. So let's take a look at carbon, for example. Carbon has 6 protons in its nucleus. So let's see if let's look at its electrons. 1, 2, 3, 4, 5, 6. Full outer shell? No, second shell holds 8. So it's missing 4. You're going to have problems finding any way to take away 4 or give 4 to an atom. 4 plus or 4 minus ions, very, very rare. But maybe we could work out that same electron sharing arrangement. Let's bring in some hydrogen. So if I bring in one hydrogen here, it can share its one electron, forming one covalent bond. Now the hydrogen feels like it has, now the carbon feels like it has 5. That's better than 4. And the hydrogen says, I've got 2, yay! Well, we can do this several more times. With 3 more hydrogen atoms. And now what do we have? Each of these hydrogens feels like it has 2. The carbon feels like it has 8. Everybody's happy. This, by the way, is why carbon usually forms 4 bonds, because it has 4 electrons out there, meaning it can form 4 shared pairs with things. And that would give it a full outer shell. So, this molecule we would write as CH4, which is methane, natural gas. Methane, of course, is flammable. And when methane reacts with other things, what you're doing is breaking these bonds and forming new bonds in something where the whole overall setup is even more stable than this. But that's a different question. So, now there is something else interesting about this. For a moment here, we need to talk about the concept of electronegativity. Electronegativity is how strongly an atom pulls on electrons. For every atom, you can talk about how strongly it seems to pull electrons toward it. What makes one atom more electronegative than another is not entirely simple, and I can't really get into it right now. I'm not totally sure I get it myself, but that's okay. What you need to know right now is of the atoms which are most common in biochemistry. Right now, I want you to know about 4 of them. Carbon, hydrogen, nitrogen, and oxygen. Those 4 elements make up a lot of what's in your body, a large percentage. So we want to talk about electronegativity with these and how much each one tends to pull on electrons, because that's going to affect how it works with these shared electron bonds. You should have Leslie Williams' book, and she uses a very nice metaphor to talk about electronegativity here. She talks about the idea of little sisters and big sisters. Of these 4 elements, the little sisters are carbon and hydrogen. And the big sisters are oxygen and nitrogen. By little sisters here, we mean relatively low electronegativity. And big sisters have relatively high electronegativity. There are a couple other elements that have more. Fluorine, for example, is the most electronegative of all elements, which actually makes it extremely reactive. If you have nothing better to do, look up the molecule chlorine trifluoride. This was the answer to a question somebody once asked an organic chemist. Is there anything where if it caught on fire, dumping sand on it would just make it worse? Yes. Look that up when you have a chance. It's fun stuff. But anyway, what this means is that if I have a bond between 2 little sisters, either between, say, carbon to carbon, or hydrogen to hydrogen, or carbon to hydrogen, those 3 bonds, since those 2 atoms both have either the same electronegativity, if they're the same element, or similar electronegativities, those electrons will be equally shared. Likewise, if I had a bond between 2 big sisters, So oxygen, oxygen, nitrogen, nitrogen, or oxygen, nitrogen. Those would also be equally shared. But if I have a bond between a little sister and a big sister, they will not be equally shared, because the big sister will pull on the electrons more than the little sister. Let me show you what I mean here. So let's go back to that methane we made, which was a carbon that had bonds with 4 hydrogens. This, by the way, is a simpler way to write those bonds than we were doing before. Rather than drawing out all the electrons and showing the shared pairs, in this kind of diagram, one of these lines stands for one shared pair of electrons, one covalent bond. Since this is a bond between 2 little sisters, these electrons are shared just about equally. Now, if we do kind of a close-up of that, where we draw in part of that bigger diagram. So here's our 6-proton nucleus, and out at one end, so we had our inner shell, and then our outer shell, and over here we had one shared electron covalent bond with a hydrogen. If those 2 electrons are shared approximately equally between these 2 atoms, if they spend, say, half their time on this side of the bond and half their time here, then this overall will be electrically neutral. If this electron spends half its time here, and this one spends half its time here, then what I've got is 1 proton and 2 kind of half of electrons, which means this side has effectively 1 proton and 1 electron. So this is neutral. If you did all the same for all the others, you'd find that methane has all of these bonds where the electrons are shared equally, where neither side of the bond is more positive or more negative than the other. A bond like that, that shares electrons, is what we call a non-polar bond. A bond where the electronegativities are similar or the same between 2 little sisters or between 2 big sisters will be non-polar. Neither side of this bond is more positive or more negative. The whole thing is electrically neutral. But that'll make a little more sense when I show you the other way it can go. So, let's go and talk about one more atom. Let's talk about oxygen, one of the big sisters. Oxygen has 8 protons in its nucleus, atomic number 8. So let's set up its electrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons, 6 in its outer shell. Its outer shell would like to have 8, so it could theoretically take 2 electrons. O2- is not a totally impossible ion, but unlikely. But it could also just make some shared electron arrangements. Let's bring in a couple of hydrogens. So here's 1 hydrogen. Sharing its electron as part of a shared pair. And here's another hydrogen sharing its electron as part of a shared pair. Now, each hydrogen is happy, the oxygen is happy, everybody's happy. So this is usually written H2O, also known as water. This is a water molecule. But let's take a closer look at that bond. This is a bond between, if we draw it this way, you can see more easily, a big sister and little sisters. So this bond here between big sister and little sister, the electronegativities here are not the same. Oxygen, as a big sister, has a higher electronegativity. These shared electrons are going to spend more time on the oxygen side of that bond. These numbers are not accurate, but they'll work as sort of a way of showing it. Let's say that these electrons spend 2/3 of their time around the oxygen and 1/3 of their time around the hydrogen. So take a look at the hydrogen side of that bond. On this side we have one positive charge from the proton and 2/3 of a negative charge from part of each electron, less than half. One positive and 2/3 of a negative means that we're left a little bit positive. This side of the bond is a little bit positive. This side is a little bit negative. Same here. Since these aren't shared equally, this side's a little positive and that side's a little negative. So each of these bonds is what we call a polar covalent bond, meaning it has a positive pole and a negative pole. Unlike the carbon to hydrogen bond, which was nonpolar, it didn't have a positive or a negative side. The bonds in water are polar bonds. It is very important that you be able to look at a structure of an atom and identify which bonds in it would be likely to be polar and which would be nonpolar. That's a really important skill that you will be tested on. It's important because it has a big effect on how these molecules interact with other molecules. And here's why.